Eduardo Mansur is a PhD student at the Université du Québec at Chicoutimi, which I'm going to call UQAC, so I don't have to pronounce that again, under the supervision of Dr. Sarah Jane Barnes. He completed his bachelor's and master's degree at the University of Brasilia, where he worked under the supervision of Dr. Cesar Ferreira Filho at this university. In late 2017, he started his PhD at UQAC. His research stems from mineral chemistry, focusing on the distribution and role of some metalloids during the formation of magmatic sulfide deposits. So one of the objectives of his research idea is to start to understand how different processes are recorded by sulfide minerals. And ideally, if we can use this understanding for exploration, targeting in the future. So with that in mind, I'm going to invite Eduardo to give his talk. And after that, we will have a Q&A session. So everybody's invited to post their questions in the chat of this Zoom session. Eduardo?
So thanks very much for the introduction, and hi everyone. I hope you can hear me well. Well, as the talk was saying, I'm basically, before starting, I would like to thank everyone from our hub. Actually, it's been amazing. I mean, I've been following your work, and thank you very much. It's pretty nice to have someone like putting stuff together and letting us like to be able to communicate, especially right now. So really appreciate it. Thank you very much. As it was introduced, my talk will be consisting of trace elements and sulfides, and I'll try to do basically an overview. So that's basically a compilation of what we have done, people have done over, let's say, past 20 years probably, and we're quickly going through some processes. Before starting, I would just like to thank my supervisor, Sarah Jane Barnes, and Charlie Duran, a colleague that helped us putting the data together, and he started a compilation actually. So basically a good part of what we are going to present is thanks to him as well. So we can go straight into it and say, why do we laser sulfides in the first place? Why are we interested in doing that? And there are three main reasons. The first one is, as was introduced, is to understand the processes leading to the formation of magmatic sulfide deposits, nickel, copper, and PGE deposits. This has been done over the past years, and where I think everyone is trying to go from now on, it's whether sulfides can be used as indicator minerals. And what do I mean an indicator mineral? Is like, for example, we here have a sample. These were sulfide grains from till samples. So you can see, I mean, there's pyrite, there's chalcopyrite, but you do not know, okay, we have no texture relation, we have nothing, but can we look at the composition of the sulfides and say, okay, this comes from a hydrothermal deposit, this comes from a magmatic deposit, or even what would be even more interesting is, this comes from mineralized rocks versus barren rocks. So that's, I believe, from now on where people will start going. You can also use for metallurgical purposes, but I'm not going to talk. I'm going to concentrate on the processes and a little bit where you can use it as indicator minerals. So where do we have data from sulfides from? Basically, people have analyzed the main PGE and nickel copper deposits in the world. This include like Sudbury, Stillwater, Bushveld, Great Dykes, different complexes from deposits from Bushveld, and Norilsk, so among others. But I mean, the big names people have analyzed, so we kind of have a good database to start looking at. And where do we find in these deposits? We can have a very simplified scheme of an intrusion here, layered intrusion, mafic or tramafic rocks, where you can have different kinds of deposits in different parts of the intrusion. So normally you can have disseminated ores. This is from Voisey's Bay here in Canada. You can have some disseminated globules within silicate minerals, so pretty nice sulfide dissemination within the upper portions or in the margins of the intrusion. Whereas if you go a little bit down into the intrusion, the textures may vary a little bit. You can start getting this net texture sulfides, and by this we mean this interconnection of sulfide grains within silicates. The sulfide can migrate through the silicates, but this is normally, they remain still connected within the silicate grains. This is normally a transition like close to disseminated sulfides, but in the middle portions, and a transition, let's say, to more what we find in the bases of the intrusions, which are more massive sulfide deposits. Massive sulfide deposits, as the name says, it's pretty massive sulfides, and you have like a pretty higher proportions of sulfides. Although you can have some silicates within those rocks, like the silicates will not touch each other. It's mainly only sulfide minerals. This can be divided into what we call iron-rich or copper-rich, or you normally refer as well to the iron-rich as copper-poor versus copper-rich deposits. In this iron-rich or copper-poor deposits, the assemblage is mainly pyrrhotite and iron sulfide and pentandite and nickel sulfide, although you can find minor chalcopyrite. Whereas when you go to these more copper-rich bits, again, this is an example from Pichinga and Vozes Bay. So you can have more copper-rich minerals, cubanite, chalcopyrite, as well as pentandite. Finally, a different kind of textures that you also find is something that is more related to the country rocks. So you have this nice example here from Sudbury in the footwall of the intrusions, where you call the vein ores. These are mainly massive sulfide bodies, copper-rich sulfide bodies, where you have cross-cutting host rocks. So basically injections of sulfide ores within the country rocks. Just also some examples from the Norilsk deposit in Russia, where you have this more brecciated association of sulfides and the country rocks. So basically, that'll be it's a pretty generalization. These are kinds of textures, but I mean, you see that the assemblages that we find, they're pretty common there. So can we differentiate from these kinds of deposits or the processes going through? And before that, we have to quickly go through how do these things form. This kind of deposits form. You normally have a silicate, mafic, ultramafic liquid, which is going to interact with country rocks. You're going to incorporate some xenoliths together with some sulfides when you're getting. So this sulfides, this xenolith starting to get melted. You incorporate the sulfides. What is cool is that initially the sulfide will be, let's say, a sedimentary sulfide minerals. So they have different compositions. Then they start to interact with the silicate liquid and collect a wide range of chalcophile elements. Among them, I mean, the ones that we concern more normally, nickel, copper, cobalt, PGEs. But then we collect all these minerals and we start crystallizing the sulfide liquid. So the sulfide liquid is going to first crystallize more high temperature, what we call MSS, which stands for monosulfide solid solution. It's basically an iron-rich sulfide. So some elements like rhodium, iridium, osmium, nickel, cobalt, they are compatible with this MSS and they get incorporated. You still remain with this copper-rich liquid. This copper-rich liquid is going to be enriched in platinum, palladium, what we call tabs, which stands for tellurium, arsenic, bismuth, tin, antimony. And in these cases, you can either start crystallizing your copper-rich liquid or you can squeeze it out from the intrusion. That's how you're going to form those examples that we saw in the copper-rich veins within the country rocks. So you can either remain into an equilibrium crystallization, and then you are going to stay with crystallizing ISS, which stands for intermediate solid solution, which incorporates some elements, but also platinum, palladium, and this group of elements, the stabs, they remain into the later most fractionated liquids. When the temperature keeps dropping, you form this interstitial liquid crystallized as platinum group minerals, and this high temperature ISS and MSS sulfides exsolves into the phases that we see in the rocks like pyrrhotite, pentandite, chalcopyrite, whereas the ISS mainly exsolves into chalcopyrite and cubanite. And what we end up having as a final product, it's the textures that we see in different deposits. This is just an example from the Norilsk. What is cool here is that in the same deposit, we have the entire migration from copper poor to copper-rich ores. So what you see is that the assemblage doesn't change that much. You still have pyrrhotite, chalcopyrite, and pentandite. However, you get an extensive fractionation. So how can I distinguish when am I looking at a chalcopyrite from a really less fractionated rock hosted within an intrusion, or am I looking at a chalcopyrite that is from the country rocks that's been like really fractionated? How do we track these previous steps? And we have to access the mineral chemistry, and there are two ways of doing that, many ways, two ways that I'm going to talk. Just an example, you can either laser individual sulfide grains. So for instance, you can laser given pyrrhotite and you'll get an individual composition for one element or for one mineral at once. Or what you can do is that you can perform, as we did here, you take your laser, you put your sample into the laser, you perform different lines, you combine it, and you ended up having a map of the distribution of these elements. I personally like it because it provides like a quick idea of which mineral is responsible for hosting different elements. So here an example, we have the spirotite in the background, the exsolution flames of chalcopyrite and pentlandite, and we see, okay, nickel, of course, is hosted by pentlandite, but also cobalt and palladium also, they go straight into pentlandite. Those more compatible elements that we saw, ruthenium, molybdenum, they go into pyrrhotite, which was exposed from this high temperature sulfides, whereas for sure copper, but also zinc, cadmium, they prefer going into chalcopyrite. Another example, we see, again, we saw that palladium is the main element that goes into pentlandite, but also platinum will straight partition, and all the platinum that you have normally would go into pentlandite. Some other elements, again, all the compatible elements, osmium, iridium, they go into pyrrhotite, whereas more incompatible elements will prefer chalcopyrite, such as indium, tin, tellurium. And what is nice about these maps is that when you're lasering in the individual sulfides, you're getting the composition of the elements that are in the lattice of the sulfide. But when you're getting an aerial distribution, you can see the variations. And for instance, lead, bismuth, thallium tends to concentrate in the edges. So you can get information in the individual concentration of the mineral, but you can also get information on the distribution, the spatial distribution. I mean, there's any remobilization, this zonation, so that's the kind of information that you can get with those. Okay, we see that the sulfide liquid has all this extensive fractionation. You go from copper poor ores to copper rich ores, but how can we track this? And we can track, how can we differentiate if a given mineral is coming from any of these ores? Before doing that, we have to get a parameter to understand how can we track the fractionation of the sulfide liquid. We can use this ratio, platinum palladium over the IPGEs. And basically, we saw that these elements increase their concentration, whereas these decrease with fractionation. So just an example from the rails, this ratio in whole rock will be from 10 to 20 in copper poor, and they go up to 5,000 in copper rich. So it increases. It's kind of a magnesium number that we're going to look just to track the fractionation. So what we did, we compile all those deposits that we have, including all the deposits that I've shown you. And we took, for each point here, we're taking a rock sample. We take the PGE concentration in whole rock. So this is going to track us how fractionated are the rocks. The more towards the right are more fractionated ores. And then with laser ablation, you take one mineral, and then you see, okay, this mineral, what's the composition of a given element? What you see is that you have a cryptic variation, like the elements that are compatible, they decrease during the fractionation, but some other elements, they increase during fractionations. Palladium, tellurium, they get more concentrated into the sulfide minerals, more you get like these ores crystallizing, basically because they are incompatible with the crystallizing elements. But although they are incompatible, one thing that is nice is that, okay, but if we still need the whole rock to track fractionation, how can we use them? And our ultimate goal is not to have a whole rock data. And we see that although, for instance, some elements increase during fractionation, like tellurium increases, selenium increases, but tellurium is more incompatible than selenium. So, okay, so this means that during fractionation, your concentrations of tellurium are going to increase way more than selenium. This means that the selenium-tellurium ratio will change. Say, can we test that? Yes, we can. So we take the whole rock ratio to PGEs and just test the selenium-tellurium ratio. And we see that progressively more fractionated ores, if you look only at the sulfide grains, that's a pentlandite, but you can use any kind of, you can use a chalcopyrite as well. You only at this ratio, and this ratio will reflect exactly if your sulfide is crystallizing from a more fractionated or less fractionated liquid. This means sulfides with selenium-tellurium ratios that are pretty low are crystallizing from those more really copper-rich ores that really gone to an extensive fractionation. So, such as those from, let's say, the Sudbury footwalls. Whereas the ores that are selenium ratios are in sulfide grains that are pretty high, crystallized from those less fractionated copper poor ores that hosted within the intrusion. So you see this decrease. You can also go back one step before and say, okay, we saw the crystallization, but can we also get some information on crystal assimilation or the degree of which the sulfide liquid interacted with the silicate liquid? And yes, you can do, if you want to trace, for example, crystal contamination, you have to look at concentrations of elements that have a low partition coefficient into the silicate, the sulfide liquid. let's say the sulfide liquid, it's going to attract all the chalcophile elements, the sulfur-loving elements. But some elements, let's say arsenic, antimony, their partition coefficient into sulfide liquid is like 1 to 10, so they're pretty low. They do not like sulfides a lot. Whereas others, like the PGEs, their concentrations are pretty high. I'm not going to show in detail, but if you want to trace crystal contamination, just look at the concentrations of arsenic, antimony. This is likely chalcophile elements, and then the higher these concentrations, more are found in more contaminated deposits that went through a more extensive contamination. Whereas if you want to trace the R factor, the amount of which this sulfide liquid interacted with silicate liquids, you're gonna have to look at the other spectrum of the elements, so the more highly chalcophile elements, because these elements, as soon as they see the sulfide liquid, they jump right straight into it. So their concentrations, if you interact with large volumes of magma, they'll be way higher. How can we compare different R factors? One of the ways that we can do, again, that's a generalization, but you can compare massive sulfides from nickel-copper deposits to disseminated sulfides from PGE deposits. Just some examples here are massive sulfides from the Norilsk deposit, whereas there are some disseminated sulfides from Merensky Reef at the Bushville or at the Norilsk 1 intrusion. And these disseminated sulfides, they've interacted with way larger volumes of magma relative to the massive sulfide. So what we see is that we can differentiate both types of deposits, basically looking at concentrations here. Just an example of palladium or rhodium in pentandite, again, can be used for different highly chalcophile elements in different minerals as well, is that the circles, the PGE deposits, they tend to have way higher concentrations of these elements. So if you have a different given grain, you can differentiate if it's coming from a Ni-cu-PGE deposit or PGE dominated deposit disseminated sulfides. So if you go back to our first question, the message on the processes, I mean, I cannot extend all the processes here today, but what we can see is that once you laser your sulfides, you're getting a wide range of elements. And you can trace all these processes here. I mean, we went through just crystal contamination, a factor, or the fractional crystallization. But what you have to do is just look at different elements. I mean, if you want to look at crystal assimilation, look at slightly chalcophile elements. If you want to trace for R factors and then differentiate between nickel-copper and PGE deposits, look at highly chalcophile elements. Also, other processes, I mean, you can track PGM at solution or pyrite formation by alteration, but these are more detailed and I haven't entered in detail here. The thing is, can we also use base metal sulfides as discriminants for the source? That means indicator minerals. Yes, that's just one example from pyrite here. We can differentiate the fields that I'm going to show for hydrothermal deposits. They comprise IOCG, VMS, porphyry, so it's kind of a compilation of deposits. Although you can differentiate very well within the deposit, for the purpose here, I'm just creating a big field for them, which differentiates from magmatic sulfide deposits. And just as the compilation, you can see like magmatic pyrites are higher in cobalt, lower in antimony. Hydrothermal pyrites tend to be lower in cobalt and higher in selenium. So you can differentiate your pyrite grains, either they come from magmatic or from hydrothermal deposits. Other sulfides that we're trying to use, chalcopyrites as well. Again, hydrothermal fields, it's comprising many different deposits. The work by Luke George, pretty amazing, distinguishing these kinds of deposits. But all of them, they do separate pretty well from both nickel-copper and PGE deposits. So, I mean, you can look at some elements to distinguish between magmatic and nickel-copper and PGE deposits, but you can also use other ones to distinguish between hydrothermal and magmatic deposits. So before I leave you, I just want to show you, call your attention to one example that has been done with this. Is an application that was done. That's here north of Quebec in Canada. And that's two areas close to the core zone and Labrador Trough here, some granitoids close to the Labrador Trough. And you can see in the right, all those black spots, these are till samples that were collected in the area. So all the till samples, they were treated and sulfide grains were handpicked. So they made pretty heavy concentrated minerals and then collected some sulfide grains from the samples, mainly pyrite and chalcopyrite. Following that, they've analyzed some of these grains. You can use, again, that's just another diagram for discriminating if you're from the hydrothermal chalcopyrites that were founded with signature for hydrothermal. And the signature was like more recrystallized stuff from VMS or CDEX. But also what was nice is that you took some pyrite grains, and then the pyrite grains, the idea is that, okay, we have some pyrite grains that have a magmatic composition, whereas we have other pyrite grains that have a hydrothermal composition. What is nice, you go back, you check, okay, where do these grains come from? You go back to the area and you check the till samples where you found those grains. You use your ice flow directions and you can retrace where these till samples came from. So ultimately, you can get to some sources for these grains. And what was nice in this study, if anyone is interested, is that we managed to find like a source for the magmatic grains with a signature, which was different from the source, potential source for the hydrothermal grains. So this is still something that has to be tested if anyone asks, okay, did you find anything in the area? I mean, we don't know, but we found different compositions, we retraced, and they pointed to different areas. So that's available, and that's, I guess, what the direction that things should go with this kind of studies. I mean, you start understanding the processes, you understand the composition, and ultimately you try to apply it somewhere. Is it going to work? I mean, it's something that has to be tested, but it's the kind of effort that we're doing. Some next steps that I think should be nice doing in this domain for magmatic sulfides. I mean, there's a lot of activity in the hydrothermal field that I'm not even able to, I'm not an expert to talk about that, but in magmatic sulfides, what we found, for some reason, people haven't analyzed deposits hosted in comatites. So we would be not, they have, but it's only one deposit. It would be nice to see, okay, can we look at the composition of a sulfide grain and tell if it's coming from more mafic or trophic intrusions or comatite flows? So that's an information that's still missing. Another thing that's still missing and could be potentially nice is, can we track post-magmatic alteration? I mean, we are looking at this more pristine deposits, but can we differentiate, okay, we have this magmatic pentlandite. What is the effect when you deform the deposit and the host rocks? What's the effect on the composition? Can we trace, okay, this is coming from a more deformed or not? New discriminant diagrams, probably using more robust and statistical methods. And what I think it will be like the most interesting thing one could do right now, it's to start analyzing barren intrusions. So people have concentrated mainly on deposits, they're studying ore deposits, but I think what will give like a lot of contribution is, okay, let's look at the intrusions that we know there is no deposit, we haven't found any deposit, so let's look extensively on the sulfides from them. So if we can look extensively, can we separate like the barren from the mineralized intrusions? I guess that's the main thing to be done. And surely more analytical developments will increase it. They'll make things like quicker and cheaper, hopefully. That's where it gets things more attractive. So you can get, like, as I said, you trace different processes with different elements. So if you can get more elements in your same analysis, that's kind of an advantage thing. So yeah, that's what I had to say. I hope I haven't like talked for too long. And if you have any questions, we can discuss, but if for some reason anyone wants to also send me an email, just feel free. I'll be more than happy to reply. And yeah, thanks very much.
Thank you so much, Eduardo, for such an interesting talk and perfectly timed. Really was very, very good. I know there's going to be a lot of questions, but before that, I want to ask Libby if she has some comments and some questions to ask.
Yeah, so thank you, Eduardo, for a really interesting talk. It's fantastic to see people developing more techniques to help with assessing indicator minerals and fertility of these kinds of systems. It's been something in the region of 10 years since I've had to look at Ni-Cu-PGE deposits, and we're just getting back into that globally. So this is definitely research that we are going to look at, which leads into my question. One of the things in my role is we're obviously looking for competitive advantages. We're looking at things that can give us answers about a project quickly and help us make decisions in a business critical time period. So I'm curious how long it takes to do these kinds of analyses. I mean, you mentioned the Labrador Trough study. I don't know if you have an idea of what the time period was for analysis, what the limits are on access to LAICPMS labs for this kind of work, and how you'd envisage a junior company maybe incorporating this kind of research into their exploration workflows.
Yeah, that's great. That's great. Thanks. I mean, I guess it depends. If you go to the, just to quickly answer, I guess this was a 1 year project, 1.5 year project, if I remember well, from the time it was approved to the results. And this includes like preparing like paper and all this stuff. So if you just want like quick results, it can be significantly shorter. What is the bottleneck for doing that? It's not the laser part. I mean, the laser part is pretty quick. What is the bottleneck for doing that is treating your pre-concentrates. So you get your till samples, you're going to have these heavy minerals, and then you're going to like take your grains and analyze. Analyzing and reducing the data is pretty quick, because for this kind of study, for those who may be used with laser ablation, I mean, you do pretty like, let's say, detailed study. You really look at your grains, you really look at your signal, and you're really trying to see what you're doing. For those, what you do is that you just laser and integrate and get the result. So you do not, let's say, waste your time in a respectful way, looking, okay, am I including, like in the magmatic sulfides, am I including a PGM? Am I lasering this? Do I have absolute win? You don't care. You just laser your grains, integrate the signals, and get it. And that's the kind of result you can get. I mean, when you get these inclusions and this stuff, although they cause a difference, they not in this scale. So that's one of the bottlenecks. The other one is how big of an area you want to do. There have been studies in Sudbury for this indicator minerals that people look in a 10-kilometer area. So it's way easier. I mean, if you look here, it's a pretty huge terrain. So it surely will consume you more time. But it's not, I mean, it's something that will be applicable. I mean, it's said in a junior company, I guess the best approach to do that is do not start from scratch and try to discover the word. I would say just try to talk to people that have databases. And I mean, there's this group from George Baudouin at Université Laval that they're trying to generate large databases. So I mean, how are you going to use it? It's another thing, but there's a lot of information available. So I will say, given the cost of all the exploration things, I guess the cost that you would have to do this, it's worth a try. I mean, you just put some like days of laser, you surely will find someone who's interested in doing that and giving it a try. So that's it. I guess the main thing is just do not be concentrated on details, just get the rough idea, and then from that you work out.
Perfect, thank you.
Thank you, Eduardo, and thank you, Libby. Libby, do you have any more questions, or we can proceed with some that we're getting from the public?
I think let's hand over to everybody else, and then if I do have one more question if we have time, but let's hear what everybody else has to say.
Absolutely. So we have a question from our public asking if, for Eduardo, did you find any trace elements or ratios that indicate sulfide saturation occurred too late? Like, for example, that a large amount of nickel fractionated into olivine prior to extensive sulfide saturation.
Not in sulfide grains, not looking at sulfides, because that's the thing that I'm saying that may be answered if you have different hosting rocks. Because I mean, most of the information are from layered intrusion. So one thing that will be nice is that having cases from more variably fractionated rocks, so you can try to access the information from the silicate liquid looking at that, but nothing. I can't come up with something right now with that way now that you can track the timing of sulfur saturation. No, I can think about it. No, not right now.
Okay. Thank you, Eduardo.
Yeah.
We have another question from our YouTube viewers that is asking if we can expect a low temperature or evolved magmatic sulfide assemblage with millerite, pentlandite, chalcopyrite, etc.
Yes, you can. You can, especially if you I haven't talked about, but I can quickly show you. When you get into more altered stuff, you start forming pyrite. I mean, that's one of the ways that you do. I mean, you can form pyrite either by, I need my pointer. You can form pyrite either by alteration of sulfide minerals, or you can form pyrite by exsolution from MSS. And what is nice is that these two, they differ. So when you have pyrite from alteration, which will be, let's say, that's an example from Lac des Îles, but you find in other locations as well. is that they show nice zonation patterns, so you cannot differentiate in terms of textures. But what you see is the concentrations of IPGEs, like pyrites that, like ruthenian, rhodium, pyrites that are solved from MSS, they tend to be higher in IPGEs relative to pyrites that have been altered. So that's a way that you can distinguish if it's an altered magmatic sulfide or if it's something that's, say, hydrothermal signature, I mean, remobilization and then reprecipitation of this stuff. So yeah, you can differentiate. I don't know if that answers the question, but that's what you can do with pyrite and for this.
Thank you, Eduardo.
Yes.
I know that Neil has a question also. So Neil, you can ask your question.
Hey, Eduardo, that was awesome, man. Maybe it's a bit of a two-parter. I think we've started to understand a lot more about the physical processes that are taking place in these sorts of deposits now.
Mm-hmm.
And going back to the concept of the R factor, which Tony Naldrett was key in developing, are we seeing anything that isn't really jiving with how we think about these? I mean, in your results, is there something really that you weren't expecting, or is everything to the book, to what?
Yeah, there are not necessarily related to those new developments into the fractionation and all this stuff. Some stuff that are pretty, but this is kind of known for a while, but I cannot understand pretty well why. It's the general. Let me just skip the contents of some PGS in some places, like with this current model, because there's going kind of a revolution into the layered intrusion world, where people are questioning either you have this big magmatic chambers and things going, or either you're having like different pulses. And there have been like propositions that actually layered intrusions are a pile of seals that going through. But some of this stuff, I mean, when you look at, these are data from Stillwater, the JM Reef, so sulfide deposits from there. And what do you, so this guy's here. So what do you see is that you have up to 1% of palladium into this bentonite. So if you take the current model that the high R factors relating to interaction and collection of different sulfides, I mean, you will need like a huge amount of silicate magma to scavenge all this PGE. So I mean, that's kind of nice to think about, because what is nice is that you're looking from a huge system, but how does this happen? I mean, you have different pulses of magma that has been like reabsorbed and then recrystallized, reabsorbed and recrystallized. And that's where I guess this physical processes are kind of interesting work. So yeah, that's one of the stuff that I kind of don't understand. How do you put that much of palladium into a sulfide liquid? I mean, in the current models, you would need like 10 kilometers of magma and interact your sulfide with the whole thing. And that's kind of irreal, I guess. So people will have to come up with something.
If it could just tag on to that, then if you're talking with deposits that have PGE minerals as opposed to PGs and sulfides, lactoseals, for example, or whatever, maybe lactoseals, maybe some others, how does that affect what you're seeing in your elemental ratios and your trends?
Normally, what you're going to see on that, again, sorry for been doing this all the time, so just that I go quicker. What do you see that is kind of unexpected in terms of that? That's a section from the Muransky Reef and the Bushveld, and you see that's whole rock data. So in the whole rock data, okay, there's no surprise. When you go through the barren rocks into the reef, your PGEs are high, and all your semi-metals that are also collected, they're high. That's all right. It's your chalcophile elements, they're being collected by sulfide. But then what we did is that we lasered the sulfides from all the samples going across the reef. And what he ended up finding is that although the PGE concentrations in sulfides are higher in mineralized rocks, like all the PGs, you see they're low, and then you get in sulfides from the reef, they get higher. The semi-metals, they show an opposite behavior, which is kind of weird. I mean, you see that the whole rock tellurium is higher in the reef. So why, when you go and look into sulfides, then your tellurium concentrations in sulfides are lower? And that's basically, okay, it shows the same thing. And that's basically, we understand that, and we see this correlation. The higher you have the PGEs in your sulfides, the lower you're going to have your semi-metals in sulfides. And that's like from the entire database, not from the bushville. So you have this negative weird correlation. And what we think is that because when you put a lot of PGEs into your sulfides, you're going to start like to create a chemical potential for the exsolution of PGMs, these minerals. And when these PGMs to form, they need to find some, let's say, bonding partners, and they're going to attach with the stabs, all this tellurium, arsenic, bismuth, and then they're going to deplete the minerals. So that's one nice thing that is nice is sulfides from PGE deposits, although they are constant, they have high concentrations of highly chalcophile elements, as we saw, they're pretty depleted into the semi-metals due to the exsolution of these minerals. So if you have a lot of exsolution, you're going to expect to have lower, not necessarily lower PGE concentrations, but low concentrations of tabs. Okay.
Thank you, Eduardo. And Libby, I know you had a second question.
I do, but actually we've got a question from Tom Belgrano. So I don't know if we can unmute him and he can ask that question.
Okay, I was going to let you jump in there, but just quickly, Eduardo, thanks for the great talk. Following on from Libby, a lot of companies will be sitting on huge data sets from bulk geochemical methods, both for ores and pulps and soil and till samples. Do those databases typically contain all of these elements, or is that a limiting factor, or could some of these ideas be scaled or just used on bulk data too?
I mean, one will have to check if, because this the data that I'm showing is mainly from laser, the traces and sulfides. So I'm not sure of how much they would have, someone would have in terms of, let's say, composition of sulfide minerals relative to whole rock. I mean, because this is not for the whole rock data itself. So I know that some companies are developing, like trying to develop databases for this indicator minerals. And the thing is that you do not need a huge database to do it. I mean, at this stage, what I think people would have to do is that instead of creating a huge database, is just start testing things. I mean, if developing a project at early stages, just give it a try with few samples and see what you get from that. I guess that would be my idea. I'll be more concerned with like already using what we have and what we know from sulfides and trying to directly apply it to some areas that are unknown, but more than, okay, let's take all the database that we have and rework. I mean, that would be my pick.
Okay, thanks a lot.
Okay.
Thanks, Eduardo. Libby, you want to have the final question for Eduardo?
Sure, he may not thank me for this, but you mentioned, Eduardo, that one of the things you're looking at going forward is identifying barren systems versus prospective systems. Now, this is obviously an excellent exploration tool if it can be developed. Do you have any hypotheses right now of what you would expect to see, given your understanding of the systems to date?
Yeah. What you have to look is that you have to this thing of comparing highly chalcophile elements and slightly chalcophile elements, because when you're looking for a deposit, basically you're looking at, as I said, for big systems, not necessarily big intrusions and this kind of stuff, but really dynamic and big systems. So if you're trying to look for big systems, you're basically looking for some factors like huge flux of magma and huge interaction of the sulfide with the silicate liquid. So what you have to search for, I believe, is that look at the concentrations of, I mean, you can use similar diagrams to differentiate nickel, copper, and PGE elements, something like this that we saw. This kind of stuff, I mean, you probably have the barren stuff even below. That's one of the possibilities that you can test. The other possibility is that when you're looking at your barren sulfides, you've interacted, you assimilated, but you did not have time to interact the sulfides with a lot of silicate liquids. So you will have more a sedimentary composition. So you have higher concentrations of elements with lower partition coefficient relative to the elements that are collected. So you will be basically trying to assess, did the sulfide have a lot of interaction with silicate liquid or not? That would be my hypothesis. I think that less dynamic deposits, less dynamic, so sulfides from less dynamic settings would have higher concentrations of these elements relative to the ones that are being collected. So you can kind of look at how dynamic a system has been looking at sulfide composition. And then you can try to distinguish, okay, is this a really dynamic and something that I would like to go for or not? Yeah, I guess that would be my hypothesis for testing that.
Perfect, thank you.